Okay, guys. Like I said, this is the first year where part of the biomedical optics and light tissue interaction courses are combined, and I'm realizing every time again that my timing is not quite perfect yet. So so my apologies for that. I have a couple of more slides for this for this part of the class, and for both courses we'll be talking a little bit more about Monte Carlo later on. But then for now you have a good introduction. So the previous method that we discussed was where you you know some probability density function p. You draw two random numbers to calculate a point somewhere in the graph of that PDF, and based on where the point lands, you decide whether you accept a number or not. If you accept it, then you can work with that. If you reject it, then you have to do this that process all over again. There's another approach that is sometimes possible, but which is more efficient, is where you can only need one random number to sample a probability density function. And I would like to try to illustrate that with the following example. So let's say we have two dice, twee dobbelstenen, which you throw, and you calculate the sum of the eyes. Basically, because every throw of a dice is a random variable, then the sum of the eyes will also be a random variable. And I'm also going to assume that the throws do not influence each other, so that statistically we are statistically we're going to be okay. And let's call that the sum of these eyes. Let's call that theta again. Then there are 11 possible outcomes, ranging from 2 to 12 for the sum of these two eyes, which you can obtain in a multiple of ways. So in total there are 64 ways to get to a certain value of theta, a certain value of the sum, and each of them is equally likely, because again the throw of one dice has equal probability for all faces. The throw of the second dice also has equal probability of both faces, and they are independent. So we can calculate all these. We can write just out all these possibilities. So 2 you can only get by throwing a 1 and a 1 with both dices, but 7, for example, you can get in a multiple of ways. So if you then calculate the probability density function of the sum of the eyes, then and this is going to be discrete, of course, because the sum is discrete. It's going to look like this. So there is a low probability of throwing 2, there is a low probability of throwing 12, and there is the highest probability of throwing 7. Next time you play Monopoly, you may want to keep this in mind. But of course, you already knew this. So the question is now, can we now simulate this outcome? So I want to simulate the sum of the eyes of two dice by drawing only a single uniform random number that is between 0 and 1. So I want the computer to generate a number between 0 and 1, and that is going to tell me then, okay, this corresponds to this sum of eyes of the dice. Let's say I want to simulate Monopoly, then I would need this function. The resulting output, so we're going to generate a random number between 0 and 1 as an input, so that the resulting output theta of I, the subscript I stands for just the index of the random number, we're going to do this many times, follows the required f of random, the function of the random number follows the required probability density function. And then again, the required probability density function is what you see in the graph here. So the approach would then be as follows. First, you would draw a random number. You would calculate the sum of i's when you know the function f, yet to be determined. Then you would store this value of theta I in the computer, and you repeat that until you have generated as many random numbers n as you wanted to generate. And if you're done, then you calculate the histogram of these data, so you plot that, and that should equal then this probability density function that you put in. So that's and then of course the question, the glaring omission in this graph is how do you calculate f? How do you approach that? So if we know the probabilities of a given outcome, so we know that the probability, so we knew that there were 36 possible ways of getting to an answer. We know also that there is only one possible way of throwing 2, and also for throwing 12. We can calculate the probability of each outcome. So the probability of the sum of i's being 2 is 1 over 36. The probability of the sum of i's being 12 is also 1 over 36. The probability of throwing a sum of i's of 3 is 2 over 36, because there were 2 possibilities to obtain that, etc., etc. So we could set up an algorithm to solve this sum of i's as a function of a random number as follows. We could draw a random number, and then looking at the colors a little bit, we could draw a random number between 0 and 1. If that random number would fall between 1 and 1 over 36, we would assign a sum of i's theta is 2. If it would fall between 1 over 36 and 3 over 36, so that is a total interval of 2 over 36, we would assign it a number 3. If it would fall between 3 over 36 and 6 over 36, so that is a total interval of 3 over 36, then we would assign it a number 4. And we could keep doing that up until 12. Then the last point would be if the random number was larger than 35 over 36, then we would assign a 12. And now what I did in the graph, and this is trying to visualize this a little bit, if you now give all these different probabilities, these different bars in the graph a different color, you could stack all these graphs together on the line. That is what you see on the right hand of the figure. And you could just put a scale of this uniformly distributed random number from 0 to 1 along that colored line, and wherever that number ends up, you just project down, and that is the sum of i's that you will assign. So what we basically did here is just stack add these individual probabilities of the different intervals together, which is of course very similar to calculating an integrated probability. Just adding the probabilities of a certain interval to the probability of another interval. So that is then the scheme that we can use for Monte Carlo sampling, and I'm gonna just explain the graph now. I'll refer you to the documentation that is on Canvas, and then this will be the starting point for our next Monte Carlo lecture. So I'm gonna basically going to end here, but I'll try to explain it as best as I can. So you see 2 graphs now here. The goal is to sample a probability density function p of x that is schematically drawn in the right-hand graph. So it has some interval from a to b, and it's a true probability density function. So it is normalized on that interval. That is where we want to generate. We want to generate random numbers in such a way that when we calculate a histogram of these random numbers, then it will be equal. It will satisfy this p of x. That's the goal. But what we have available in the computer is only random numbers between 0 and 1. That is what the computer generates, and these are equally likely. It is a uniform distribution of random numbers. So the probability of getting any each of them is equal. So what we can do now again is using this trick of integrated probabilities is first starting from the right hand side, we can calculate the cumulative distribution function, or the integrated probability over a given interval. So from a to a certain value of x. and then on the top, on the bottom right-hand side, you see in green you see this this area. That area is plotted on the top right graph. So the basically the cumulative distribution function of x. So p of x on the right-hand side is the probability density function of the random variable. F of x is the cumulative distribution function of f of x. So that is something that we can do for the random variable that we want to calculate. We can also do that for the random variable that the computer generates, and that is what you see on the top left. So if the probability density function for the uniform random number is constant, then the cumulative distribution function for the uniform random number is going to be a straight line from 0 to 1. And the trick is now the graphical trick that I've tried to explain with the dice, where you had the colored bars and you had on top of that you had the line of the uniform random number. Basically we equated these two and then looked down to see what the interval was. Well, we're going to do the same thing here. We're going to equate the cumulative distribution function of the random number with the cumulative distribution function of the variable that we want to find. And this dotted line is supposed to visualize that equation. So then the process, the Monte Carlo sampling principle is then as follows. I'll get to you in a moment. So the process then here is to first generate in the computer a uniform random number between 0 and 1. That's labeled RND1. Of course, because this distribution function is so very simple, then the value of the cumulative distribution function is going to be a random one as well. The probability of drawing a random number between 0 and some value is going to be equal to that some value. So there it does not change that much. Then we cross over to the cumulative distribution function of the random variable that we want to sample. So we equate these, and then once we have this equation, we try to solve for a random variable x1. It says sample, but that should be solve. There is 2 documents on Canvas. One is called Monte Carlo Notes, which writes this out. The other one is a book chapter, Monte Carlo modeling of light transport in tissues, steady state and time of flight. Time of flight is time dependent. We're not going to do that, but the steady state is basically what was in here. So we're going to do a little bit more of Monte Carlo in the BMO class and some more in the LTI class later on. I'll try to make because my scheduling is a little bit off, as you notice. I'll record some stuff, so I'll put that on Canvas and I'll notify you of that, and I'll give you at the appropriate time. I'll give you the hint to read this chapter and this document, and then we'll continue the discussion on the Monte Carlo. Then Pepijn, you had a question. You said 1 over mu is over the domain 0 to infinity. Yeah, that is correct. That is correct. So apart from the discussions from Cuvettes, if you consider transport in an infinitely wide, infinitely large medium, then the range of possible path lengths is between 0 and infinity. So that is true. That is the range. All right. Then what after this short break of earlier on, I would like to give you a little bit of a longer break, because at 3:30 Johannes is going to talk about Raman spectroscopy, which is a completely different topic. So I'm just want to give you the time to organize your notes and put them away and have a clear head for the next topic. So so I'm going to stop the recording, and but for questions, of course, you can still chat me.
Is the lecture of Johannes also via this this meeting link
Yeah,
or?
you can, he's going to log in, so you can just stay here.
Okay, cool.
Yeah.